At the end of the topic, you will be able to describe heat as a form of energy, define specific heat capacity and thermal capacity, discuss the change of state of matter, explain latent heat of fusion and vaporization.
Introduction. We know that heat is a form of energy. It flows from hot spot to cold spot. The branch of science which deals with the measurement of heat due to chemical reactions and physical changes is called calorimetry. Many physical transition and chemical reactions are connected with the production and consumption of heat. The measurement of heat energy is done with devices such as calorimeter, thermometer, and bolometer. The word calorimeter comes from the Latin word cala, meaning heat, and from the Greek word metri, meaning measure. The most primitive calorimeter was invented by Benjamin Thomson in the 17th century. In this chapter, we will discuss measurement of heat with calorimeter and some effects of heat on matter. If you keep an ice cube on your palm, how do you feel? You feel so cold because the ice cube takes heat from your palm and melts. We know that heat gets transferred from hot to cold. From this, we understand that when two bodies of different temperatures are brought into contact with one another, heat is transferred from a body at a higher temperature to a body at a lower temperature. This is the fundamental principle of calorimetry. Now, let us discuss an example for heat transfer. Take a cup of hot water. Insert a metal spoon in it. After a few minutes, if you touch the spoon and the water, you can observe that the water and spoon are at the same temperature. Heat transfer takes place between these two bodies until there is a temperature difference between them. Transfer of heat ceases when they attain the same temperature to one another. This state is known as thermal equilibrium. Let us now see the factors that influence the quantity of heat. Take two identical beakers A and B. Fill them with 100 grams and 200 grams of water respectively. Keep both the beakers on the tripod and heat them. Note the time that the water takes to start boiling. After some time, we see that water in beaker A starts boiling first. A few minutes later, water in B starts boiling. Note that the water in beaker B takes double the time than the water in beaker A. This means that the quantity of heat required to boil water in B is more than that of A, because beaker B has more mass of water than A. Thus, the quantity of heat Q absorbed by a body is proportional to the mass M of the body. Q is directly proportional to M. We will see another example. Take 100 grams of water in a container. Place it on a tripod. Note the initial temperature of water, say T1, using the thermometer. Now heat the water to 40 degrees Celsius. Note the time taken for water to rise its temperature from T1 to 40 degrees Celsius. Now continue to heat the water to 80 degrees Celsius. Note the time taken for the water to rise from temperature T1 to 80 degrees Celsius. Water takes more time to reach 80 degrees Celsius than to reach 40 degrees Celsius. This proves that quantity of heat Q absorbed by a body is proportional to the rise in temperature delta T, that is, Q directly proportional to delta T. If we combine the two equations, Q directly proportional to M and Q directly proportional to delta T, then we get that Q directly proportional to M delta T. Q is equal to M S delta T, where S is a constant called the specific heat of the body that depends on the material of the body. Now let us learn more about specific heat of materials. Take 3 beakers filled with the same quantity of water at the same room temperature. Further, take 3 balls made of aluminium, copper and lead with equal mass, say M. Immerse all the balls tied with threads into boiling water for some time. Now, transfer the 3 hot balls quickly, one each into one of the 3 beakers containing water. Stir the water in each of the beaker and observe the maximum temperature attained in each of the beaker. You will observe that the beaker with hot lead sphere dipped in it attains the highest rise in temperature than the copper sphere, which attains higher temperature than the aluminium sphere. This is because of the different characteristics of the material of the bodies. Hence, the specific heat differs for different materials. Therefore, we can say that Q is equal to M/S delta T. From the experiments, we infer that specific heat S of a body is equal to Q divided by M into delta T. Where Q is the quantity of heat in calorie, M is the mass of the body in grams, and delta T is the rise or fall in temperature in degrees Celsius. If M is equal to 1 gram and rise in temperature is 1 degree Celsius, then S is equal to Q. Thus, we define the quantity of heat Q required to raise the temperature of unit mass of a body through 1 degree Celsius is the specific heat of that body. The CGS unit of specific heat S is calorie per gram degree Celsius and also measured in kilocalorie per kilogram degree Celsius. In SI system, the unit of specific heat is joule per kilogram degree Celsius.
Specific heat capacity is an important intensive property of matter which is expressed in relation to a unit of mass. But the concept of thermal capacity is more useful as an extensive property of matter which is proportional to the size of the system. Thermal capacity is defined as the quantity of heat required to raise the temperature of an object through 1 K. Thermal capacity is given by the equation C is equal to Q by theta T. The SI unit of thermal capacity is joule by Kelvin, J by K or Jk to the power minus 1.
We know matter exists in 3 states. They are solid, liquid and gas. When we heat some solid substance, it melts and becomes liquid. The temperature at which a solid becomes liquid is the melting point of that substance. Similarly, at boiling temperature, liquids change to gaseous state. Do you know how this change of state of matter occurs? In the following slides, we will learn more about the transition of matter from one state to the other by the effect of heat. When a substance changes from solid to liquid or liquid to vapor, it consumes or evolves some quantity of heat without any change in temperature during the process. The quantity of heat given up or absorbed by a substance as it changes its state is the latent heat of that substance. It is called latent because it is not associated with the change in temperature. Latent means hidden. No change in temperature occurs in thermometer when a substance changes state even though heat transfer occurs. Each substance has a characteristic latent heat of fusion, latent heat of vaporization, latent heat of condensation, and latent heat of sublimation. Latent heat is absorbed upon evaporation and released upon condensation. Condensation is the reverse of vaporization, for example, clouds changing to rain. Latent heat is absorbed when water melts and latent heat is released when it freezes. Let us now learn about specific latent heat. We use the word specific to mean per unit mass or for each kilogram of mass. Specific latent heat can be defined as the amount of heat required to change state of unit mass of a substance without rise in temperature. Next, let us discuss the latent heat of fusion and vaporization. Latent heat of fusion of a solid substance is the heat energy required to change it from solid to liquid without any change in temperature. The latent heat of fusion of an iceberg is the heat energy needed to melt all of it. None of this heat causes temperature rise of the water formed from the ice. The latent heat of vaporization of a kettle full of boiling water is the heat energy needed to turn all the water at 100 degrees Celsius into steam.
In this topic, you have learnt heat is a form of energy transfer between two systems or between a system and its surroundings due to temperature difference between them. The amount of heat energy required to raise the temperature of 1 kg of a substance through 1 K is called the specific heat capacity of the substance. The quantity of heat required to raise the temperature of an object through 1 K is called the thermal capacity of a substance. The quantity of heat given up or absorbed by a substance as it changes its state is the latent heat of that substance.
At the end of the topic, you will be able to state Boyle's law, verify Boyle's law with an experiment, state Charles' law, express the gas equation, explain Kelvin scale of temperature.
We know gases are fluids and they can be compressed. The pressure and temperature of gases varies when they are compressed. In the late 1600s, the Irish-born scientist Robert Boyle invented an air pump. Boyle noticed that gas seemed to be springy. When gas is compressed to a small volume, he observed the pressure is increased. In 1662, he discovered the relation between pressure of gas and volume of space it was squeezed into at a constant temperature. We know gases are fluids and they can be compressed. The pressure and temperature of gases varies when they are compressed. In the late 1600s, the Irish-born scientist Robert Boyle invented an air pump. Boyle noticed that gas seemed to be springy. When gas is compressed to a small volume, he observed the pressure is increased. In 1662, he discovered the relation between pressure of gas and volume of space it was squeezed into at a constant temperature. Now let us learn the Boyle's law statement on the nature of gases. At constant temperature, the pressure of fixed amount of gas varies inversely with its volume. That is, P is inversely proportional to V. To understand this law, let us see an example. Take an air-filled cylindrical container with frictionless piston. Compress the air in the container slowly to make it smaller, without any of the air escaping. If we compress the air to half its original size, the pressure of air inside would be twice as great. If we squeeze the air in the container to 1/3 of its original size, the pressure would be 3 times as great. The rule is true only as long as the temperature of the gas is kept the same. Sudden change in pressure increases the temperature. Hence, compression or expansion should be done slowly. If the mass and temperature is held constant, then PV is constant. As the volume of air decreases, its pressure increases. Any gas which is submitted to change in pressure must obey Boyle's law and respond to corresponding change in volume. Now let us verify Boyle's law. Consider a fixed amount of gas at a constant temperature in a vessel whose height is h1, area is A, volume V1 of the container is equal to area A multiplied by h1. The total pressure inside the container P1 is equal to the sum of pressure due to the weight W1 and the atmospheric pressure, say pi. Therefore, P1 is equal to W1 by A plus pi. Initial condition according to Boyle's law is P1 multiplied by V1. Now the pressure in the gas is increased by applying more weight W2 to the piston. Now, let's say that vessel's height is h2, area is A, and so volume V2 is equal to A multiplied by h2. The total pressure inside the container P2 is equal to the sum of pressure due to the weight W2 and the atmospheric pressure, say pi. Therefore, P2 is equal to W2 by A plus pi. It is found that P1 multiplied by V1 is equal to P2 multiplied by V2, or P multiplied by V is a constant.
We have one or more gas laws called Charles' law. It is also called as the law of volumes. This law explains the behavior of expansion of gases on heating. Charles' law states that pressure remaining constant, the volume of a given mass of gas is directly proportional to the absolute temperature. This can be given in the form of an equation as V is proportional to T, pressure remaining constant, or in other words, V by T is equal to a constant. If we represent the values of volume and temperature in a graph, it would be a straight line. From Boyle's law, we have PV is equal to a constant. From Charles' law, we have V by T is equal to a constant. When we combine these two laws, we arrive at the equation PV by T is equal to a constant. The value of constant in each of the above three equations is different. The equation PV by T is equal to a constant is called as the ideal gas equation. From this ideal gas equation, we also arrive at the equation P by T is equal to a constant. In other words, volume remaining constant, the pressure of a given mass of gas is. Kelvin scale of temperature was designed by Lord Kelvin, a British inventor and scientist. It is a temperature scale where the 0 of the Kelvin scale, 0K, corresponds to minus 273 degrees Celsius. The size of one division on the Kelvin scale is the same as the size of 1 degree on the Celsius or centigrade scale. Hence, 0 degrees Celsius is equal to 273 K. Kelvin scale of temperature is also called the absolute temperature scale. Kelvin is the SI unit of temperature. To convert Celsius to Kelvin scale, the formula to be used is K is equal to 273 plus C. Similarly, to convert Kelvin to Celsius scale, the formula is C is equal to K minus 273. Let us see an example of converting Celsius to Kelvin scale and also Kelvin to Celsius scale. Example 1. Convert boiling point of water to Kelvin scale of temperature. Boiling point of water is 100 degrees Celsius. K is equal to 273 plus C. K is equal to 273 plus 100, which is equal to 373 K. Example 2. Convert 300 K to Celsius scale of temperature. C is equal to K minus 273. C is equal to 300 minus 273, which is equal to 27 degrees Celsius. In this topic, you have learnt Boyle's law states that temperature remaining constant, the pressure of a given mass of gas is inversely proportional to its volume. Charles' law states that pressure remaining constant, the volume of a given mass of gas is directly proportional to the absolute temperature. PV by T is equal to constant is the ideal gas equation. Kelvin is the SI unit of temperature.